Okay, dear colleagues, let's start our morning session. Hello to everybody who is online. Hello to our participants in our conference hall. And today, for me, it's a big pleasure to introduce Professor Kęstutis Aidas from Vilnius University. Kęstutis is a senior researcher and associated professor in Vilnius University. He did his PhD in chemistry in University of Copenhagen in 2010. Professor Aidas is author of more than 50 publications and is awarded for many professional awards. So for me, it's a big pleasure. Kęstutis, can you hear us?
Yes, I can. Can you hear me?
Yes, we can hear you and we can see your presentation now. And the title, you can see this is modeling of NMR properties of complex molecular materials by means of an integrated MD-QMMM approach. Kęstutis, you have 1 hour, about 1 hour, so please, the floor is yours, and probably we will ask you some short questions when you will tell us your lecture, and after the lecture we will have more extended questions. So,
Okay. Thank you very much. Thank you, Sergey, for this very nice introduction. I think you have a bit too good opinion about me. All right. So thank you again for inviting me to give this presentation at this workshop. And it is very unfortunate that I cannot do this. I'm not able to do this in person. I have been in Kiev several years ago, back in 2016, when there was a conference on physics of liquid matter, I think it was called. It was very interesting conference, very nice city, and of course, very tasty borscht. So I would be very happy to do it once again. But for now, we have to do it this way. So I'm here in Vilnius and you are there back in Kiev. So I will be honest with you from the very beginning. I have barely done any work on molecular, biomolecular, macromolecular compounds. I informed Sergey this in the very beginning, and well, he said, it's okay. So here I am. So really, it will not be what I'm going to be talking about today is not going to be about the macromolecular, biomolecular, macromolecular systems, but something a little bit about something else, but really related. So for quite some time now, we have been here interested in modeling of electronic properties of large molecular systems. And if any of you has ever tried any quantum chemical calculation, you know very well that things get very messy and difficult once the size of the system is increased. I mean, the larger is the molecule you want to calculate the properties of, the longer you have to wait. And eventually this time becomes so large that there is no way you can even expect to get the result. And this comes quite soon, actually. This was quite soon. And so what to do if you want to study large molecular systems, and there is a very good motivation for that, because whenever experiments are carried out, they are usually performed on the samples in condensed phases, be that a solid state or a liquid state, and gaseous samples are investigated relatively rarely. So if you have a molecule in solution, or you have a molecule in the solid state, then this molecule, of course, interacts with all the molecules around it. And in this way, the electronic structure of the molecule, of your molecule in question is perturbed, and you have to take, and the properties of these molecules then are changed compared to the properties which you would see for the isolated molecule. So you need a method to account for these interactions in the quantum chemical model if you want to compare your computational results with experimental results on an equal footing. So one way of dealing with this issue is by using the so-called combined quantum mechanics, molecular mechanics models. And the idea here is to subdivide your large molecular system, as for example, we have here some molecules surrounded by water molecules. So basically, this is an aqueous solution of some molecule. So the idea here now is to subdivide the entire molecular system into two parts. The small part and the interesting part is described by a quantum mechanical model, whereas the rest of the system, like to be the solvent, for example, that can be described by a much simpler model, for example, by classical force field. And there is a good reason why to do this, for example, because usually one is only interested in a small part of the system, the solute, for example, right? And the environment of the molecule, of the solute, then it could be really seen as being of secondary importance, and therefore one could treat it at a simpler, more coarser level of theory. So now a subdivision of the molecular system into quantum mechanical part and molecular mechanical part implies that the total Hamiltonian of the system is partitioned into three terms. So the first term here, HQM, is just an ordinary molecular electronic Hamiltonian in Born-Oppenheimer approximation. And it describes the motion and the properties of the quantum mechanically treated region. Then we have this last term, HMM, which describes the interactions between the molecules in this classical region. And then we have this very important second term, HQMMM, which describes how the two subsystems are talking to each other. I mean, how what is the model? How do we model the interactions between the quantum mechanical systems and molecular mechanical system? So, in the simplest approach, the molecular mechanical system can be represented by a set of point charges. And they are fixed, as usual in the MD simulations, for example. So in this way, the classical system represented by the point charges generates an inhomogeneous electrostatic potential, and the electronic system of the QM system interacts with these inhomogeneous electrostatic potential of the MM system, and in this way you account for the electrostatic and sort of polarization interactions between the QM system and the MM system. Now we can go a step further, and the step further would be to introduce, in addition to the point charges, also the atomic dipole polarizabilities for the molecules in the classical region. Now, these atomic dipole polarizabilities, they give rise to the induced dipole moments. And now a new physics is introduced, because now we introduce the so-called many-body effects, because the induced dipole moments, they not only depend on the charges of the classical system, but also on the density of the mechanical system. And in this way, now we account for the polarization interactions between the QM system and the MM system in a consistent manner. Right now, the two systems really feel each other, which was not the case when the classical system is only represented by the fixed point charge distribution. So therefore, this HQMMM interaction Hamiltonian can be represented by these two terms. The first term accounts for the electrostatic interactions between QM system and the MM system, and the second term accounts for the polarization interactions between the two systems. So what is the strength of the model like this? But first of all, of course, that all the molecules in the system are kept discrete, as they are in nature. And this is a bit of the criticism towards the so-called implicit salvation models or dialectic continuum models, which represent the solution or the environment of the molecule in question as a continuous dialectic medium described by the macroscopic parameter, the dialectic constant. There are others, but this is the most important constant. So, so in a way, the QMMM model is in a way a bit more natural as opposed to these implicit salvation models. And yes, although the polarizable continuum model, we have to admit, it also accounts for both the electrostatic and polarization interactions between the solute, the molecule, and the environment. With the QMMM model, there is another advantage, that the quantum mechanically described region does not have to only include the important molecule of the system, the one which you are interested in, meaning the solute. You can actually expand the QM region to include some relevant solvent molecules. And the typical example here is the hydrogen bonding. If there are hydrogen bonds formed between the solute and the solvent molecules, then it is very typical that it is very important to include these solvent molecules to the QM region of the model as well. And we will see examples of this later. So in this way, we not only improve the electrostatic and polarization interaction between this solute and solvent, but also we introduce non-electrostatic effects, and primarily polar repulsion is introduced. Also some dispersion, but because in this work we have mainly been using DFT, so you know very well that with DFT there are problems with dispersion, so it's questionable, but polar repulsion is definitely there. So that's another good thing of the model. So now, if we want to use this model for prediction of the electronic properties of molecules in condensed phases, we of course are facing one particular problem. I mean, now if we want to include the interactions between the solute and the solvent, for example, fully, then we really need a lot of solvent molecules around the solute to be included. And in case of aqueous solution, that for small solute, this number amounts to at least 250 water molecules or so. And it would be larger, even more molecules would be needed if a solute were a medium-sized molecule, for example. So that can be done, but of course, if you have so many solvent molecules, then how do you distribute them around the solute? I mean, if you have several hundred solvent molecules, then of course that the QMMM model needs to be coupled with some type of statistics. And this is where MD simulations come in. And I have seen the schedule of your workshop. I assume you have had a fair share of MD simulations in this workshop covered. So I will not be talking about the MD simulations a lot. Just let me briefly discuss how we are using the MD simulations in relation with the QMMM model for the electronic molecular properties. So exactly, we are performing the classical MD simulations, the most ordinary type of MD simulations, and the aim of the MD simulations is to sample the phase space of the system in question. So basically, once we reach the equilibrium of the system, we have the production run stage, and during this production run stage, we record the trajectory of the system. Now, if we want to calculate these electronic properties of molecules in the condensed phase using the QMM model, so what we do, we take this trajectory and we extract a certain number of molecular configurations spaced at regular intervals in time, and we perform these QMM calculations on each of these molecular snapshots taken from the trajectory. And our final results in the result of the property in question, the property which we are calculating in solution, is just the average over all the molecular configurations which we have considered in the QMM calculations. So in this way, we are kind of mimicking what really happens in experiment, especially in the NMR experiment. So when the measurement is done, it's basically, and the result is an average over the entire molecular dynamics of your sample over the time period at which the measurement has been done. So we are exactly doing the same. We are actually doing exactly the same. So in this scheme, there are several points which need to be addressed. So one thing relates to the selection of the molecular snapshots from the trajectory of the MD simulation. So one has to be assured that the molecular configurations included into this set of molecular configurations to be treated by the QMM calculations, they need to be statistically uncorrelated, meaning that the subsequent molecular configurations included to the set, they need to be spaced at fairly large intervals in time to assure that each snapshot actually brings the new statistical information to the table. And in practice, in the cases of ordinary liquids like aqueous solution, the spacing of 10 picoseconds is generally more than enough. So really not an issue here. Then there is the number of configurations to be included, because you want your statistical averages to be converged with respect to the number of configurations included into averaging. And the practice has shown that once you are sure that that these molecular configurations are statistically uncorrelated, so the number of configurations which assures converged statistical averages is around 100. Then another thing relates to the QMM model. So here one needs to select a specific quantum mechanical model in the calculations, and we normally use DFT, and you know very well there is a bunch of DFT functionals you can choose from. So some work is needed to be done with respect to the selection of a proper DFT functional, and that usually has to do with the property one wants to calculate. So, for example, certain functionals will be used in the calculation of the NMR properties. Certain functionals, maybe other functionals, will be used in the calculations of, for example, electronic absorption spectra or vertical excitation energies. Then there is the quality of the molecular mechanical potential. So the simplest case is when we only use atomic point charges to represent molecules in the classical region. You could also use, as we have been discussing, use also polarizable force fields. You can also go beyond charges in the static multiple expansion of the charge densities of the classical molecules, meaning that you can also include, in addition to the static or permanent charges, you could also introduce permanent atomic dipole moments, permanent atomic quadrupole moments, even octupole moments if needed, and so on. So something like this. And then we also need to consider the partitioning of the system into the QM region and this classical region. So if, as we have been mentioning before, if there is hydrogen bonding between the QM and MM region, I mean between the solute and the solvent, for example, then maybe these hydrogen bonded molecules need to be included to the QM region of the model as well. Okay, so with this, let me go to the specific examples. And the first example I would like to share with you is concerns something that is a bit related to the biological macromolecules. And this is the tautomerism of adenine. So adenine classically is known to exist as in equilibrium of two tautomeric forms. In aqueous solution, for example, in aqueous solution, adenine exists as in two tautomeric forms. So the canonical tautomer, which is called the H9 tautomer, looks like this, and we have a proton here as at the ninth position here, and we also have the minor H7 tautomer with a proton here at this position. And the populations of these tautomers are as follows. These are experimental results. So the minor tautomer H7 in aqueous solution is around 20% experimentally, and then 80% is for the canonical H9 tautomer. And one of the reasons why this minor, energetically less stable, if you want, tautomer is stabilized in aqueous solution is because it has a higher dipole moment as compared to the canonical H9 tautomer. Therefore, in the polar solution, we have, of course, favorable dipole-dipole interactions, and therefore, the population of the H7 tautomer is substantial in aqueous solution. Now, in dimethyl sulfoxide, the population of the H7 tautomer maybe is a little bit smaller as compared to aqueous solution, but nevertheless, it is still there. Now, back in 2001, there was this paper by Laxer, who performed the 15 nitrogen NMR measurements of adenine dissolved in dimethyl sulfoxide. And based on the broadening of this nitrogen NMR signals, the conclusion was made that there might be a third tautomer, which we call here H3 with the proton at this position here, present in the DMSO solution of adenine. And the population of it was not estimated experimentally, but there were other following works, especially theoretical works, which made a few steps further. They actually made predictions that H3 tautomers should also be present in aqueous solution of adenine as well. And even the mechanism of tautomerization was considered. So we thought we could also do a little bit of work on our part of our own as well. So the idea here is, suppose if we have these three tautomers in aqueous solution, what we could do, we could use this MDQMMM scheme, as we have just discussed, to simulate or to predict the NMR, the nitrogen shielding constants of all three tautomers of adenine in aqueous solution. And the tautomer averaged shielding constant would then be calculated according to this equation, meaning that the tautomer is of course is a very rapid process in comparison to the measurement, to the NMR measurements. So basically we assume only the equilibrium between the H9, H7 and H3 tautomers, and X here represents the molar fraction of the H7 tautomer, Y represents the molar fraction of the H3 tautomer, and of course 1 minus X minus Y is then of course the fraction of the canonical H9 tautomer. So we can simulate separately the shielding constants of each of the tautomers in aqueous solution. And then we can construct the tautomer average shielding constants in this particular manner. And then, of course, we can construct, based on this shielding constant computed for the nitrogen nuclei, then we can construct the tautomer average spectrum. And then by comparing this tautomer average spectrum, which we have computed, to the experimentally measured spectrum, we can actually deduce what the populations of the H7 and H3 tautomers should be in order for the calculated spectrum to match the experimental spectrum in the most accurate fashion. So this is exactly what we did. We performed the MD simulations of all 3 tautomers in aqueous solutions. We used the QMMM model to compute the nitrogen NMR shielding constants for each of these 3 tautomers. And in this way, the QM region has in fact been expanded to include these hydrogen molecules, which are hydrogen bonded to the adenine in the QM region. So we have this covered. And then we have constructed the nitrogen NMR spectrum of each of the 3 tautomers separately, which is shown here. And here at the bottom panel, you see the experimental nitrogen NMR spectrum, which is taken from this work. I mean, this is a spectrum of adenine in aqueous solution. So now if you compare the computed nitrogen NMR spectra of each of the tautomer to the experimental one, you can clearly see that there are qualitative mismatches between them, meaning that indeed tautomerism is in action in this case. And really what we see here is in the experimental spectrum is the result of the averaging over all the tautomeric forms of adenine which are present in solution. So we did exactly that. We tried to construct the tautomer average spectrum. Here, the top 3 panels, again, they show the same NMR spectra as seen before, corresponding to the NMR spectra of each of the tautomers separately. At the bottom here, we have the experimental spectrum. And in the middle here, we have the theoretical tautomer average spectrum. And now these 3 numbers here on the left, they correspond to the population of the canonical H9 tautomer. The second number corresponds to the population of the tautomer H7, and the last number corresponds to the population of the tautomer H3. So you can see now that once we have constructed the tautomer average spectrum, everything comes into place, so to say. The computed NMR spectra, now they agree very well with the experimental spectra in qualitative terms, but also to a large extent in quantitative terms as well. So you can see that maybe only the NMR signal of the first of the nitrogen atom at the first position here is somewhat overestimated in the relative spectrum, but otherwise the agreement between the computed spectra and the experimental spectra is really good. And you can see that we estimate that the best agreement is obtained something around here. So where we have 83% of the canonical tautomer H9 and 17% of the minor tautomer H7, exactly as the experimental data would suggest, more or less. And you can also see that for population of the H3 tautomer is 0 in all these cases. And this is the reason why. So we have tried now to fix the population of the tautomer H9, of the canonical tautomer H9 of adenine to this 83%, which we found was optimal. And then we have changed the populations of the H7 and H3 tautomer. So we started with 17% for H7, 0 to H3, and then we distributed the population from H7 to H3. And you can see the evolution of the relative NMR spectrum. You can see that the signals from the nitrogens at positions 1 and 7, they start to approach each other. And for the population of the tautomer H3 as small as 3% or 4%, these two signals interchange with positions, and you can see that these changes in the NMR spectrum, they are not compatible with the experimental spectrum. So based on this, we reached the conclusion that this minor tautomer H3 of adenine, it probably is not formed actually in aqueous solution of adenine, or at least very short-lived, that it doesn't have any impact on, for example, the NMR spectrum, nitrogen NMR spectrum of adenine solution. So this is one of the...
I'm sorry, may I ask you just...
Absolutely.
For curiosity, the second line, it looks like more close to the experiment because we have two lines. In the case of N3, 4%. So we have, or it just seems to be.
I'm sorry, Sergey, maybe I did not follow you.
The second line in the spectra, the second.
Here?
No, up from the.
Here?
Yes, here.
Okay.
You can see we have two lines, and the experiment also has two lines. So at least qualitatively, it looks.
There are three lines, three in one, and the up one, 7 in one.
Ah, I see. So different. I see. So this is different signals.
Yes. So.
Okay.
The point comes to the ordering of the signals. So you can see that here the positions of the nitrogen NMR chemical shifts of nitrogens at positions 1 and 7 is interchanged. And even if you go further, if you increase the population of this H3 tautomer still further, then you could expect that the signal of the nitrogen at first position would go to the right here, to the right with respect to the signal number 3, and the signal of the nitrogen at position 7 would approach that of the nitrogen at position 3, which is not what we see in experiments, right? Which is not like that. So based on this, we think that this tautomer H3 of adenine probably is not really formed in aqueous solution. Okay, so this was back in 2010, so fairly old study here. So let me show you something what we have been doing more recently. And here, very recently, we have been involved in the modeling of structural and NMR properties of ionic liquids. So ionic liquids are fascinating materials. These ionic liquids are basically molten salts. So basically, they are formed, they are made out of ions entirely. We have cationic cations and anions forming these ionic liquids. And because of the very particular molecular structure of particularly cations, because you can see here I show the example of typical cations which are used to produce the ionic liquids. They are very asymmetrical, they are very bulky, meaning that ion packing is kind of statically difficult, and therefore these materials are liquid at room temperature. Therefore, we have this term room temperature ionic liquids. And here on the right, you can also see all the various ions which could also be used in combination with different cations to form the ionic liquids. So basically, you can now see that by combining different cations and anions, you can really form a myriad of different ionic liquids. And each of these ionic liquids may have different... Okay, yeah. So we can have different types of ionic liquids with different properties, meaning that you can actually, at least in theory, tune your ionic liquid for the specific applications one might need. And indeed, these ionic liquids have already found applications in different fields. They are used as electrolytes, they are used as solvents in chemical synthesis, they can be used as catalyzers of certain chemical reactions, they can be used, for instance, for the purification of water from toxic metals in wastewater, so in separation chemistry basically, but they also have some very important biological applications. For example, it has been shown that the mixtures of certain ionic liquids with water, they serve as a very good preserving media for proteins or possibly even DNA. So meaning that the shelf life of proteins in these particular solvents is much longer as compared to the ordinary aqueous buffer solution. So that's one thing. Another thing is that ionic liquids may actually enhance the biological activity of certain enzymes. And other applications. For instance, if you have in drug design, one of the issues is the solubility of the newly formed drug molecules. So if they are insoluble in water, that is a pain, that is a problem in actually using these molecules as drugs. But if you have, for instance, certain mixture between a biocompatible ionic liquid and water, the solubility of these drug molecules might be increased dramatically. So these ionic liquids here, when they act as these so-called hydrotropes, which increase the solubility of certain organic molecules in aqueous media by orders of magnitude. So really fascinating applications. But now, if one wants, if one is willing to even widen the areas of application of these ionic liquids, one needs to understand the interactions and the structure of these ions in the ionic liquids at the molecular level. And this is where we came in. So let me, let me briefly, because I can see my time is almost over. So let me briefly just talk about one particular study which we have done. Maybe I will skip this one. Maybe this is a little bit less interesting. Maybe this one is more interesting. So here we have considered the mixtures between this ionic liquid, the 1-butyl-3-methyl-imidazolium cation and chloride anion, and this cation is shown here. The structure of this cation is shown here. So the mixtures between this particular ionic liquid and water. And our study has been motivated by the following experimental results. So here on the diagram on the left, the evolution of the hydrogen NMR chemical shifts of water is shown. The evolution on the composition of the mixture, of the binary mixture between water and this particular ionic liquid. So this 0 corresponds here to pure aqueous solution. And you can see once ionic liquid is introduced into the solution, the chemical shift of water drops dramatically. At around the molar fraction of the ionic liquid of around 0.3, 0.3, the chemical shift of water starts to increase again. So we have this non-monotonic evolution of the chemical shifts of water with the changing composition of the mixture, which is quite curious. And it, of course, reflects that some type of molecular organization is changing with the changing composition of the mixture. Here on the right, we have the evolution of the chemical shift of the proton at the second position in the imidazolium ring. And we can see that with the introduction of the ionic liquid, or with the diminishing content of water in solution or in the mixture, the chemical shift of this particular proton is increasing quite dramatically from less than 8.8 to more than 10. And that's really a huge increase. It's a huge increase. So these experimental results, they really show that some dramatic structural changes are happening in the system. So we have tried to use our MD simulations combined with the QMMM calculations for the NMR, hydrogen NMR chemical shifts in this case, to address this experimental findings. So we have performed MD simulations of pure ionic liquid and of its mixtures with water. And we have had a 50-50 solution mixture, 50% molar fraction for ionic liquid, 50% of molar fraction for water, also 25% for ionic liquid and 75% for water. And we have also performed just the simulations of the liquid water, which we will use as a reference for the chemical shifts of protons in water molecules. So here we see some spatial distribution functions for which show how chloride anions are distributed around the imidazolium cations in the system. So we can see that chloride anions, they attack basically the imidazolium ring from 3 different sides. So most importantly from this side, which corresponds here this site is in the vicinity of this proton at the second position in the imidazolium ring. And this C2H2, so-called C2H2 bond, it is the most acidic in this system, and therefore it forms the strongest hydrogen bonds with the anion. Now we also have these two CH bonds. They also form hydrogen bonding with the chloride anions, as shown here, but but they are a bit less strong. They are a bit weaker as compared to the hydrogen bonding at this site here. So we can see with the diminishing or with the increasing content of water molecules, we can see that basically by comparing these figures, we can see that water is somehow replacing gradually the chloride anions in the vicinity of the imidazolium ring. We still have some hydrogen bonding between imidazolium and chloride anions in these mixtures where water content is quite high, but we can also see that we also have waters approaching imidazolium ring in these systems as well. And another very characteristic structural results which we have got is the formation of complexes between chloride anions and water molecules, and this is how they are represented. You can see here that these green blobs, they represent basically the statistical distribution, or if you like, maybe the probabilistic distribution of finding chloride anions in the vicinity of the water molecules. So we can clearly see this double hydrogen bonding formed between chloride anions and water molecules. So now these MD simulations were performed, and we have extracted a certain number of molecular configurations from the molecular trajectories, and we used the QMMM calculations by using DFT, basically based on DFT, to compute the NMR, the proton NMR spectrum of imidazolium cation. And here in this figure, we show the comparison between the computed relative proton NMR spectrum of imidazolium cation in the neat liquid with the measured NMR spectrum, with the corresponding measured NMR spectrum. And here we have this red line. This is a unit light, and this line is only drawn to facilitate the comparison between theoretical and experimental spectra. So basically, if this point here is on the line or close to the line, that corresponds to a good agreement between the theoretical and experimental results. And if the point were above the line, that would imply that theoretical model overestimates the corresponding chemical shift. And if the point is below the line, as for example here, then the chemical shift is underestimated by the computational model. So you can see here that the computed relative NMR spectrum corresponds to the experimental one fairly well. It definitely agrees in qualitative terms, but in many cases also in quantitative terms. Even the spacing between the chemical shifts of protons at 4 and 5, at positions 4 and 5, which is something less than 0.1 ppm, is reproduced correctly here by the model, and only the chemical shift of the proton at position 2, which is in fact the most interesting and the most relevant, is in fact underestimated by the model, and quite severely, by more than 1 ppm. So this is quite an issue actually, but I will not go into the details here. I just would like to also to tell the scale of the QMMM calculations which have been done here. So in these calculations, not only the central imidazolium cation was included to the QM region, but its entire first solvation shell has been treated quantum mechanically as well. So you can imagine these were really quite large quantum mechanically described regions. So these were really heavy calculations. Nevertheless, we were able to perform them. So this is quite a nice comparison, with the exception, of course, with this chemical shift for the position of the hydrogen atom at position 2. So this is so far so good. But when we move to the mixtures, mixtures between this ionic liquid and water, things, they do not become that pretty. So here we have calculated the shielding constants of water molecules in the mixtures of in its mixtures with the ionic liquid. So here at the bottom we have the shielding constant computed for neat water, and here we have 3 different populations, 3 different compositions of the aqueous mixture of this ionic liquid, corresponding to 75, 50, and 5% of water. So now we can see that if we go to this particular case where we have 75% of water, so you can see that the isotropic shielding constants of the protons of water molecules in these particular liquids is in fact larger than the isotropic shielding constant computed for liquid water, implying that the chemical shift of water molecules in at this particular composition of the mixture will be lower than seen in the liquid water. So we indeed have reproduced this effect, the lowering of the chemical shift of water molecules with the increasing population of the ionic liquid in the mixture. So this is quite well. And then we have also the mixtures between the water and the ionic liquid with the very high content of the ionic liquid. And we can see that protons in water molecules, which are forming these hydrogen bonds with chloride anions, as we have seen before, they are very much deshielded, implying very high chemical shifts, and therefore we can see that this increase in the chemical shift of water molecules is understandable, because once you move here to the right, when we go from very small clusters of water molecules to separate water molecules interacting with chloride anions, and by averaging over the entire ensemble, we of course then can expect the increase in the chemical shift of water molecules, because at this position we will have more water molecules interacting with chloride anions rather than water molecules interacting among themselves. So qualitatively, at least, we can understand the evolution of this particular curve. We have also performed the shielding calculations of shielding constants of protons at the second position in the imidazolium ring, and we can also see that the higher the content of the ionic liquid, the lower the shielding constant, implying the higher chemical shift. So in the ion pair formed between the imidazolium cation and the chloride anion, the proton at the second position is shielded more than in the case where this imidazolium cation is forming the hydrogen bond with water molecules, and therefore we see this gradual increase in the chemical shift of the proton at the second position with the increasing content of the ionic liquid in the mixture. Okay, so with this, let me finish my presentation. I would like to again thank Sergei in particular for inviting me to participate in this event. I hope you have had a good one, and I'm sure you did. And also in particular, I would like to thank my teams, my young people who are working with me, PhD students, and now young doctor. Without them, all these studies wouldn't be possible. And of course, for all my collaborators. So thank you very much. And I'm very much open for the questions. Sorry for taking so much time.
Thank you, Kęstutis. Colleagues, we just received the message from our colleagues from Kharkov. There is a missile attack. There are some problems in Kharkiv with internet. So I wish to our colleagues the fortitude, and I would like to give opportunity to ask the question, first of all, to colleagues from Kharkiv. So please, probably somebody wants. Probably Marina Kasevich wants, Professor Kasevich. Okay. So we have some message was in chat.
Thank you for
Okay. Yes, there is one question in Zoom, please.
Hi. I saw in your presentations ethanol molecule moved on different vibration modes. And
yes.
Yes. Can you please show this?
Absolutely, sure. Yes, here.
I mean this. And the question is the following. Why do you use this mode? How do you calculate these mode frequencies? I mean, do you use just linear variant of potential or non-linear approximation of potential? And
Okay.
in which method do you use? Classical or quantum mechanical?
Thank you very much for the question. So this figure here was just to illustrate the fact that we are using classical molecular dynamic simulations for the sampling of the phase spaces of the molecular systems which we are studying. So as you know, the molecules in the classical MD simulations, they move on the potential energy surface, which is completely described by a classical expression, which involves intramolecular terms as well as intermolecular terms. So intramolecular terms, they account for the vibrations of the molecule in question. So we have stretching vibrations, we have stretching vibrations like here, we have bending vibrations like here, and we have also some torsional vibrations as illustrated here. And all these vibrational motions are described by the classical force field, which is very well known. I did not include the analytical expression, but I'm pretty sure you know it very well. So this particular figure was only put here just to illustrate that. Of course, I didn't mention. I admit that. Sorry, but in terms of the calculations of vibrational spectra, at least what we have currently available for us here in Vilnius, we cannot predict the vibrational spectra of molecules by using MD simulations coupled with the QMMM model. And the simple reason is this, because by using quantum chemical methods, the vibrational modes or vibrational frequencies are only defined at the equilibrium points of the molecule on the potential energy, I mean at the minimum of the potential energy surface. And in the MD simulation, of course, the molecules are never at the minima of the potential energy surface, meaning that these vibrational spectra, then conceptually, they cannot be calculated as one is used to by optimizing the geometry of the molecule and computing these vibrational modes, for example, in the harmonic approximation, right? So with MD-QMMM approach, at least what we have here in Vilnius, we are unable to do it, but I have seen papers where people try to do it, and I'm pretty sure it's done in a theoretically sound manner. So that would be my answer, I hope.
Sorry, I'm interested on anharmonic approximation of such calculations. Do you know something about it?
No, I'm sorry. I have never done. I haven't done much work on vibrational spectroscopy as such, and definitely not on the anharmonic
Thank you
calculations.
very much. Thank you, yes.
Okay, and other questions? Probably in conference hall, please, Dr. Kęstutis.
What software do you use for MM and QM calculations?
Thank you. So our MD simulations, now we very often use AMBER, the well-known code, but we have also tried the code M Dynamics. I think you might know it as well. And before, I mean, some time ago, we also used the code called MolSim. MolSim is not a very well-known MD program, but it has certain advantages. On one hand, it allows performing really strictly rigid body molecular dynamic simulations, which in certain situation is advantageous for us, but also it allows for using explicitly polarizable simulations in the explicitly polarizable force fields in VMD simulations, which might also be very good. But otherwise, now we in many cases use simply AMBER. Now for the QMMM calculations, we use a Dalton quantum chemistry program.
Thank you.
Thank you.
Okay, if there is no other question, so let me ask the question. A very nice result you showed about calculations using this very advanced method, and I just wanted to specify in the case of ionic liquid in different mixtures, you took into consideration the interaction of ions water with molecule, with imidazolium molecule, and also I suppose it can be important the interaction between different molecules, positively charged molecules. So they have some tails.
Yes.
Tails are flexible. Probably some influence maybe from this side.
Yes, you are completely right. So these ionic liquids, they are very particular systems, particular materials which exhibit what is called the nanostructural organization. And this is a very specific to these ionic liquids. So if you take, for instance, imidazolium cation, like for example shown here, it consists of a polar part with polar imidazolium ring, as well as non-polar alkylic chain here. And we also have anions which are also polar in nature. So what happens in many cases is that you get the domains, the polar and non-polar domains in the ionic liquid, where you can see that the non-polar alkylic chains, they somehow aggregate into non-polar regions, and the polar regions are composed of, for example, these polar imidazolium rings together with the anions. And this is very characteristic. And now if you also introduce water, then water molecules, they are also polar, then they contribute to the polar regions. And maybe I could try, I don't know how well this is visible, but here you can see in this figure, this is a snapshot basically of the simulation box from the MD simulation. These blue regions, they correspond to the apolar, to the cations, and they correspond to cations. Red are water molecules and green are chloride anions. And you can probably see quite well that we have certain regions where we have blue cations and certain regions where we have the polar chloride anions as well as water molecules. So we actually see this segregation between the polar and non-polar domains in the MD simulation very well.
In MD, in classical MD simulation?
Yes, this is in classical MD simulation.
I see. Thank you. Thank you.
Thank you, Sergey.
Okay, so if any other questions? If you have...
Yes, if I may.
Yes, please.
Yeah, thank you for the lecture. And one of the slides you mentioned that you've included water molecules in your QMMM, right? In your QM region. So I want to ask, how did you include those water molecules? Because
yes.
Wouldn't they move around, you know, the simulation box?
Oh yes, we do, of course. But then the algorithm is usually as follows. Well, you can do in different ways, but one of the ways would be to take your central molecule and define a certain radius around a particularly chosen site in that central molecule. And then we say, if at least one atom of the solvent molecule is closer to that particular site in the central molecule, closer than the defined cutoff radius, we introduce that solvent molecule in the QM region. And we do it from configuration to configuration. Another approach would be to predefine a particular number of solvent molecules to be included to the QM region close to a particular site in the central molecule as well. So we have quite a flexibility here, but the motivation between the selection of the solvent molecules to be included to the QM region is, of course, the convergence of the property one is calculating. So, for example, if we are calculating here maybe the chemical shift or isotropic shielding constant of a proton at this position, and this proton, we know very well that it is involved in hydrogen bonding with chloride anions, for example, or water molecules, then of course we need to include these into the QM region, of the model. So so that's because this really has an effect. This really has an effect on the shielding constant of this particular proton. So we need to be sure that we have included enough molecules to the QM region that once you include one more additional, the result for the shielding constant of the H2 proton here would be unchanged. So that's basically how you decide how many you should include.
Thank you. And the thing is, I've tried to do this with Gromax-Orca combination, and I could never do it in this way because it always forces me to decide specific molecules I want to include in QM. So again, but what you're saying about defining the region as a certain cutoff distance from your molecular center, do you know if it's only allowed in like Ember software or somewhere else? You know?
So I suppose you are probably talking about QMMM MD simulations.
Yes,
I mean,
yes.
Okay, so this is, just let me, maybe I was not completely clear. Here we have done completely classical MD simulations as usual. And when we only use QMMM calculation in connection with a response theory to calculate the spectroscopic properties or whatever electronic properties there is. So we don't have this issue as you do. I can imagine your problem because, as you say, the molecules, they are moving. So yeah, that's an issue. I don't have any good answer to this problem because I don't have experience here, unfortunately.
And
all right, thank you very much.
Yes, James, I would like to say probably you visited the lectures yesterday, and we had lecture by Dr. Zdarevsky, and he gave a lecture on QMMMD. But not Orca Gromax, he told about Orca NAMD.
Yeah, that's one lecture I missed.
Yes, it was yesterday. Professor Aidas, Kęstutis, I just would like to thank you once again. Let's thank you for very interesting lecture. And, now we go to other lecture in our program. The following lecture will be in Ukrainian. So